Hello everyone, my name is Ivan Fernandez and I'm here with my colleagues Pablo and Jorge, and we are here to present our project in the subject of numerical methods. Our work focuses on the numerical resolution of the Advection-Reaction-Diffusion Equation. Second, we will detail the numerical application, including our discretization and integration strategies. Finally, we will present the results and conclusions, specifically analyzing stability, steady-state solutions, and the multi-grid method. Let's start with the mathematical model. We are solving the one-dimensional linear advection-reaction-diffusion equation. As shown here, the rate of change of our variable u is determined by three mechanisms: diffusion, advection, driven by the velocity field, and a linear reaction term. We also have an external source term r. The problem is defined on the domain from 0 to 1. To close the system, we apply Robin boundary conditions at both ends, which combine the function value and its spatial derivative using constants alpha and beta. We also specify an initial condition, u0, to start our transient simulations.
Thank you, Ivan. I will now explain how we solve this numerically. We choose the finite difference method on a uniform grid. We use central difference for both the first and the second derivatives to ensure second-order accuracy. A key part of our approach was the God point method. By introducing fictitious nodes outside the domain, we could implement the Robin boundary conditions without reducing the order of accuracy of our scheme. Using the method of lines, we substitute the spatial approximation into the PDE. This transforms the continuous equation into a semi-discrete system of ordinary differential equations, expressed as the one in the screen. The matrix A represents the discretized spatial operation, while the vector P accounts for the south term and boundary conditions. To illustrate the structure, here is the system for a simple grid with n equal to 4. You can clearly see that matrix A is triagonal. This structure is very important because it allows us to use highly efficient storage and solving grids later on. The first and last rows are slightly different because they incorporate the ghost points from the boundary conditions. With the spatial discretization complete, we move on to the numerical application, specifically how we integrate the systems in time.
We implemented four schemes to compare their performance. For explicit methods, we use explicit Euler and Hoynes method. For implicit methods, we selected Crank-Nicolson and BDF2. As you can see from the equations, the explicit methods are simple to calculate, while the implicit methods require solving a linear system at every step. The major challenge here is stiffness. The diffusion term creates large negative eigenvalues scaling with 1 over the difference in x squared. For a grid of n equals 20, the stability limit for the explicit Euler is extremely restrictive, around 0.00125. Since our test time steps were larger than this, we predicted that the explicit methods would fail. Our test confirmed this prediction. When we ran the simulation with n equals 20, the explicit Euler and Hoyne methods exploded due to instability. However, Crank-Nicolson and BDF2 remained perfectly stable for all time steps, validating that implicit methods are necessary for these types of diffusion-dominated problem.
Now let's look at the steady state, where the solution does not change with time. This simplifies our problem to a linear system. To solve this, we implemented the Thomas algorithm. This is a direct solver specifically for tridiagonal systems with a linear computational cost, which is much faster than general solver. We also solved the problem using the finite volume method. Instead of focusing on points, finite volume methods balances fluxes across control volumes. We use a vertex-centered approach and approximate the fluxes at the cell interfaces using central differencing. This ensures that mass is conserved locally within each volume. Here is the matrix resulting from the finite volume method for n equals 5. If you compare it to the finite difference matrix Pablo showed earlier,
The structure is nearly identical. Both methods preserve the three-diagonal dominance characteristics of the 1D diffusion equation. Moving to the results on a fine width of n equal to 200, this plot shows the error versus the time step. The explicit methods, blue and red lines at the top, show hue error due to instability. In contrast, the implicit method, yellow and purple lines at the bottom, are stable and show a clear slope of hue, confirming the second-order convergence in time. Here, in the steady state profile for n equal to 100, the solution is smooth and monotonic, increasing from the left boundary to the right. It effectively balances the advection, diffusion, and reaction forces along with the sinusoidal short time to satisfy the Robin boundary conditions. We compare the result of finite difference versus finite volumes on this slide. As you can see, the blue curve and the red dashed curve overlap perfectly. The difference between them is effectively zero. This proves that for this specific 1D problem with a uniform width, the two methods are algebraically equivalent.
Finally, we applied a multi-grid V-cycle to accelerate convergence. The red line shows the standard Gauss-Seidel method, which stagnates because it cannot smooth out low-frequency errors. The blue line represents our multi-grid solver. It converges rapidly, reducing the residual to 10 elevated to -9 in just 14 cycles, demonstrating superior efficiency. To conclude, we have successfully analyzed the stability of various time schemes, validated the steady state using the Thomas algorithm, and demonstrated the equivalence of finite difference method and finite volume methods for this case. We also showed the power of multi-grid for acceleration, and thank you very much for your attention.